Minimax just released a 1 million token language model that's free, open source, and challenges models that cost over $100 million to train. Built for just $500,000. The standout feature is M1's massive context window, 1 million input tokens with 80,000 token responses. To put this in perspective, you could feed it the entire Harry Potter series and still have room left over. While OpenAI's GPT-4 handles about 1/8 of that capacity, and Claude 4 Opus manages 1/5, M1 provides breathing room that other public models simply don't offer. Even Google's Gemini 2.5 Pro matches the million token input, but caps responses much shorter, and the popular open-source DeepSeek R1 tops out at just 128,000 tokens both ways. Handling such massive context usually crashes into the transformer's fundamental problem: attention costs that explode as sequences grow longer. Minimax solved this with two breakthrough innovations. First, they implemented a mixture of experts design, essentially 32 specialist submodels sharing one brain. Each token activates only a handful of these specialists, so while the complete model contains 456 billion parameters, only 46 billion work at any moment. Second, they replaced the traditional every token looks at every other token approach. Attention with lightning attention, a linear technique that keeps computational costs nearly flat as prompts expand. 7 standard transformer layers sit atop each lightning block, preserving the architecture's strengths while doing heavy lifting in lighter mode. The efficiency gains are dramatic. When M1 generates a 100,000 token response, it uses only a quarter of the floating point operations that DeepSeek R1 would require. At 64,000 tokens, it's under half. This efficiency translates directly to training costs. Minimax completed their entire reinforcement learning phase in 3 weeks using 512 NVIDIA H800 cards, costing roughly $535,000. Compare that to DeepSeek R1's $5 to $6 million budget, or GPT-4's estimated $100+ million training cost. The secret weapon is CISPO, Clipped Importance Sampling Policy Optimization. Traditional PPO reinforcement learning avoids instability by cutting off large gradient steps for unlikely tokens. Unfortunately, those rare tokens often contain crucial wait, let me rethink moments that real reasoning depends on, strangling creativity. CISPO flips this approach. Instead of cutting gradients, it caps important sampling weights while letting every token contribute. In Minimax's tests, CISPO achieved the same math contest scores in half the training steps of its closest competitor. Before reinforcement learning began, Minimax conducted 7.5 trillion tokens of pre-training on a carefully curated dataset, 70% STEM, code, books, and explicit reasoning content. They then ran supervised fine-tuning that injected long, chain-of-thought answers, teaching the model to naturally lay out solution steps. Only after this solid foundation did reinforcement learning kick in. The training curriculum mirrors human learning progression. First came verifiable tasks with rule-checkable answers. Tens of thousands of competition-level American invitational mathematics exam problems. 53,000 generated logical puzzles from cipher grids to Sudoku variants, and 30,000 competitive programming challenges. For real software engineering experience, they mirrored GitHub issues into sandboxes, where models must read bug reports, locate broken files, write patches, and prove fixes work through passing unit tests. The second phase tackled tasks with single correct answers that resist simple rule checking, detailed science questions, and tricky factoids. Here they trained GenRM, a generative reward model that learned to pick better responses by comparing human-labeled answer pairs. Finally came open-ended conversation and instruction following, where GenRM used simple three-way judgments against reference answers selected through Swiss round tournaments among multiple strong models. Throughout training, engineers monitored for length bias. Reward models sometimes award extra points just for longer replies. When the policy started stretching answers without accuracy gains, they paused, recalibrated the reward model, and resumed. They also solved critical technical challenges. Switching the final language model head to 32-bit floats fixed probability mismatches between training and inference, while a simple rule prevented infinite loops by stopping generation after 3,000 words of extremely high confidence output. The team gradually expanded reply limits from 40,000 to 80,000 tokens, only opening each gate once perplexity stabilized and real generations approached the ceiling. Each expansion required dataset rebalancing, since bad answers tended to run longer than good ones in later stages.